Hello, everyone. Our project focuses on developing an intrinsically safe barrier concept for a company called Proportion Air for the Proportion Air QB electro-pneumatic pressure controller. In hazardous environments like Class 1, Division 1, equipment must prevent ignition by limiting electrical energy, and our goal was to build a proof of concept barrier that ensures voltage and current stay below the limits specified in IEC 60079-11, specifically keeping open circuit voltage under 29 volts and short circuit current under 150 milliamps. This project matters because commercial IS barriers are expensive, difficult to customize, and often sealed or potted, which limits design flexibility. Our work explores how a university team could begin developing an internal, intrinsically safe barrier solution.
For the electrical portion, we started by building a breadboard prototype of the barrier using Zener diodes, resistors, and protective fuses, replacing the core energy limit principles used in the intrinsically safe systems. We tested the circuit under different inputs of voltages and measured the key parameters, uh, for example, in open circuits or in short circuits. Um, we then compared our results to the energy limiting thresholds that were defined in the documents Proportion Error gave us. Our prototypes demonstrated a basic ability to limit electrical energy into a safe range. Although the breadboard designs are not certifiable, these tests show the fundamental intrinsically safe concepts working as expected, and this laid the groundwork for the future PCB-based development.
For the mechanical part of the project, we focused on the barrier's physical enclosure, which plays a critical role in maintaining safety. Using SolidWorks, we designed the top cover of the enclosure and evaluated its strength using a simulation based on IEC 60079. This standard specifies that enclosure must withstand the impact of a 1 kilogram striker dropped from a height of 0.4 meters, which is equivalent to 4 joules of impact energy. We applied this impact load to the weakest area of the cap and examined the resulting stress, strain, and displacement. The results showed that all stresses remained below the material's yield strength. There were no plastic deformation, and the rib side geometry significantly improved stiffness. This means the enclosure design is likely to survive mechanical impact testing required for real-world intrinsic safety certification. This provides useful pre-compliance insight for future teams who may fabricate the full enclosure.
So, in summary, our team successfully built and tested a functional breadboard intrinsically safe barrier, demonstrated that it can limit electrical energy, and performed early mechanical validation of a potential enclosure design. We also identified key limitations. Commercial barriers are sealed and difficult to study, and full certification testing was beyond the scope of this semester. So, for future teams, the next steps include designing a full PCB, fabricating a complete enclosure, and performing full IEC and FM safety tests. Thank you.